Good morning, my dear students. In the previous class, we discussed about the potential energy of the system of 2-point charges in the presence of an external electric field. Today, we will discuss about the potential energy of the dipole in the uniform electric field. Students, we know that electric dipole is a pair of equal and opposite charges separated by small distance. And already we have studied that when dipole is placed in the uniform electric field, it will experiences torque. The net force acting on the dipole is 0, but it will experiences the torque. In this class, what the dipole has the potential energy in the uniform electric field processes that we are going to be discussing. See here, there is a uniform electric field. There is a uniform electric field. Uniform means electric field is same at every point on this surface. Now I will place one electric dipole. Say it is plus Q, it is minus Q. The dipole moment is P. The direction of the dipole moment is from negative to the positive. This dipole makes an angle of theta with the uniform electric field. In the uniform electric field, this dipole experiences the torque. Say that the positive charge experiences the force in the direction of the electric field. The negative charge experiences the force opposite to the direction of the electric field. Right? This positive charge experiences the force in the direction of the electric field. This negative charge experiences the force opposite to the direction of the electric field. So this dipole, because of the opposite nature of the charges, net force acting on this dipole is 0. It will tend to rotate the dipole in this way. It will tend to rotate the dipole. It is in the rotatory motion. Right? So, if I suppose you say that I take this as a dipole and place it in here, this dipole experiences torque in the presence of the external electric field. Uniform electric field, net force on activity on this dipole is 0. So, suppose that there is a positive charge and there is a negative charge. This positive charge experiences the force in this direction. This negative charge experiences the force in opposite to the direction of the electric field. So, it will tend to rotate like this. It will tend to rotate like this. Right? Because of the nature of the charges, it will take rotatory motions. They are equal in magnitude and opposite in direction. So, it is rotating in this way. Like this. One force is in this direction, another force is in this direction. So, it is taken the clockwise direction. Right? So, whatever the dipole experiences the torque, that torque has to be neutralized. That torque has to be neutralized. How it can be neutralized? By just applying the external torque on it. By applying the external torque on it, we can just neutralize this torque. So the work done say that from theta 1 to theta 2, that work done is stored as what? Potential energy of the bed. That work done is stored as the potential energy of the bed. That is what we are going to be studying. Alright, so here we will consider an electric dipole of dipole moment P is equal to Q into 2A placed in uniform electric field. The net force acting on this dipole is 0, but it experiences a torque. And is given by tau is equal to P cross E. This is the expression for the torque we have studied in the last chapter, that is electric charges and field. When the dipole is placed in the uniform electric field, the net force on the dipole is 0. It will experience the torque, and the torque is given by the expression tau is equal to P cross E. The magnitude of the dipole is given by tau is equal to Pe sin theta. Tau is equal to Pe sin theta. So it is the dipole moment, E is the uniform electric field, theta is the angle between the P and E. Now, as I said that this dipole is rotating now. Now, to neutralize this torque, whatever that this torque is experienced by the dipole has to be neutralized. Suppose an external torque is applied. Suppose an external torque is applied to just neutralize this torque, through small angle, d theta. This dipole is experiencing the torque in the presence of the uniform electric field, so it will rotate like this. When it is rotating, now I will apply the external torque on this dipole to just neutralize, to just overcome its original orientation. Alright? So I will apply the external torque on the dipole. Whatever this dipole is rotated in this way, now I will apply an external torque to a small distance like this to neutralize this. So whatever the torque is applied on the dipole to a small angle with theta without acceleration. So the amount of work done by the external torque, the amount of work done by the external torque is given by is given by W is equal to integral over theta 1 to theta 2 tau into d theta. The amount of work done to neutralize this dot through a small angle d theta, say that small angle is varies from theta 1 to theta 2. We know that integral over theta 1 to theta 2 tau is nothing but what? Pe sin theta. Pe sin theta into d theta. This P is dipole moment, E is electric field. Both are constant. Dipole moment is constant and E is constant. So I will take it outside. So it is Pe integral over theta 1 to theta 2 sin theta into d theta. Right? So I write Pe into the bracket, integration of sin theta is minus cos. So limits over theta 1 to theta 2. So W is equal to, I write minus of Pe cos theta 2 minus cos theta 1, substitute the limits here. So for natural choice, say that theta 1 is equal to pi by 2 or 90 degree, and theta 1 is equal to simply theta, then W is equal to cos 90. Theta 1 is equal to 90 degree. So cos 90 means what? 0. Theta 1 is nothing but theta. So this expression becomes what? Minus of E cos theta. Right? So this work done is stored as potential energy. This work done is stored as what? Potential energy. Therefore, we write U is equal to minus of Pe cos right? So this is the expression for the potential energy of the dipole in the